Hello everybody, I'm Abbas Omidi, and I'm here to present our recent paper, Unsupervised Domain Adaptation of MRI skull stripping trained on adult data to newborns. So this is a paper of VACVI conference. I'm the first author and I'm presenting this paper on behalf of my fellow authors. So let's jump to our abstract. Skull stripping is an important first step for analyzing MRI images. So you can see an example of skull stripping. Basically, it means to remove the skull and keep the brain itself. So we have some deep learning based supervised models such as the unit model. They have shown promising results on automating the brain segmentation process and the skull stripping process. However, they need some labeled data for us to be able to train those models on them. But when it comes to newborn MRI data, there are no publicly available data sets with brain masks. Also, manually segmenting a brain is time consuming, labor intensive, requires a lot of expertise. So we cannot easily capture some newborn MRIs and label them and feed them to a unit model. And you may ask why we cannot train a model on adult images and then test it on newborns. So we have tried that. It's not possible due to the large domain shift between adults and newborns data. As a result, we need an efficient method for skull stripping the newborn's MRI images. So in this paper, we present an unsupervised method for skull stripping those newborn images. So one major challenge for us is the gray matter and white matter tissue in newborn brains are immature, so they are not similar to the gray matter and white matter of adult brains. So as you can see in picture A, this is a normal MRI image of an adult, and picture C, this is a normal MRI of a newborn. So for an adult, it's slightly lighter, you can see in the red square, but for newborn, it's darker. So we mitigate this domain shift caused by this difference in white matter, gray matter contrast. So we perform some data augmentation process which inverts the contrast between white matter and gray matter in an adult brain MRI. So you can see the results on picture B. Now we have a contrast inverted MRI of an adult, which is more similar to newborn compared to the original MRI. So we performed this data augmentation, and then we fed these new generated images to a unit model, but not a simple unit model. So this is a figure of our model. So as you can see, we have two learning loops here. So the first loop, you can see it in green. It's a standard 3D unit model. So it starts with an image. It has encoder and decoder. It extracts the features and try to generate a brain mask for it. So it's pretty standard and a normal 3D unit. But we have a second loop which has a focus on discriminator. So discriminator in pink, you can see, it aims is to discriminate between adult images and newborn images, which means that we ask our discriminator to only tell us whether this image belongs to an adult or to a newborn. It's a simple discriminator. So our first training loop or unit, everything is a standard. So forward propagation and backward propagation is pretty normal. But when it comes to our discriminator training loop, it's a bit different. So during the forward propagation, everything is okay. So we extract the features in our encoder, then we pass those features, our bottleneck here, to our discriminator and ask our model to discriminate between them, whether they are for adult or they are for newborn. In backward propagation, we update the parameters of our discriminator pretty normal. So we make our discriminator stronger and stronger at every epoch. But when reaching this gradient reversal layer, we multiply a negative constant to our gradient. So basically, with multiplying this negative constant, we are negating our gradients. So this leads our encoder, our feature extractor parameter to be updated reversely, like to increase the discriminator loss. So what happens when we increase our discriminator loss? Basically, we are making our features in a way that they are not discriminative between newborns and adult. So we are forcing our feature extractor to learn domain invariant features, to learn more generic features. So that's the catch of our method. So in our first training loop, we are keep learning how to create brain labels, brain masks for our images. And in our second training loop, we discriminate between adults and newborns. Then we apply that gradient reversal layer and we update our feature extractor reversely. So we ask it to increase the loss and we ask it to extract some features which are similar between newborns and adult, so the discriminator cannot discriminate between them. So our results, you can see our results here. So our proposed method obtained the best metrics among unsupervised methods. So there is a 50% improvement in dice coefficient and 35% improvement in Hausdorff distance metric compared to the second best unsupervised method, which was a unit model with domain with this method of domain adaptation. And in comparison to the very cutting edge supervised models, our model outcomes stands like very near the SOTA model. So it's only 0.7% less than HippODIP and 2.7% less than SynStrip. Having said that, both of those models are supervised models. It means that they have already been trained on a dataset of labeled newborn MRIs. So that's why this comparison, it's not a fair comparison probably, because they are supervised models. But the reason that we compare our model to those supervised models is that, first of all, to show our model results is very similar to those supervised models. And secondly, there are no other methods to compare with. So there are no models for skull stripping of newborns which are unsupervised. So thanks a lot for your attention. And that's it from me. Yeah.